Okay. Um, Hello, welcome back to another Math Counts meeting. Today we're continuing 2012 Nationals, and we're on number 24 sprint, I believe. Let me zoom in on this. Okay, for equilateral triangles, ABG, BCH, CDE, and DAF are constructed inside square ABCD, as shown. Points E, F, G, H are the vertices of the triangles that lie within square ABCD. What is the ratio of the area of square EFGH to the area of square ABCD? Express your answer in simplest radical form. Okay, at first, this looks pretty complicated. You have a lot of lines and stuff. But you just want to maybe break it down a little bit. So first, identify where the triangles are. So this is ABG. This is BGH right here, or BCH right here, and then this is CDE and this is DAF. So our first four triangles, they're like equilateral triangles going into the square, and it goes like more than halfway, right? And then the tips of the equilateral triangles um, are the vertices of this new square. And you want to know what the ratio of the area of this square is to the area of our larger square. And notice that we're not given like any side lengths because we're looking for a ratio. So we can just set an arbitrary side length and then find the ratio with that. Or we can set it to a variable, but I'll just set the outside square length to be 1. And then what we need to do is we need to find the side length of the inside square, and then we put a ratio from it to 1 and we square it because we need to find the ratio of the area. Okay. Now you have to think about how you're going to get the side length of the square. This is going to require some thinking and like geometry skill, and yeah, basically you're just gonna have to try to find like a clever solution to this. There's no really like, I don't know, like intuitive way to do this. And so the way to do this, or one way you can do this, is you can get the length, you can get the altitude lengths of the equilateral triangles, right? The base is 1. You can definitely get what this is. Well, this is just going to be what, √3/2, right? Since this is going to be 1/2. Since this is just 1/2 of the base, and then here we have a 30, 60, 90 because we're separating an equilateral triangle. So then this is going to be √3/2. You can see I can line up. So if you look at like this middle strip here, and then I have E right here, and then I have G right here. So my E is my top of one of my equilateral triangles, right? So I drop this down. This is going to be √3/2, right? And then if I drop G down here, this is also going to be √3/2. So this section is √3/2, and this section is √3/2. So what we can do is we can wait. Oh, okay. And then, no, my bad. Okay, and then this whole. Okay, yeah. Okay. No, okay, my bad. Okay, so this whole strip is 1 long, right? Because this is just going to be what, this side is just going to be parallel to this side of the square. Okay, and then so this side is this whole side is 1. So then what you could do is you can add up these two lengths, right? The two root 3/2s, and then you're gonna get this whole length plus an additional inside length, right? You're adding these spots by 1, and you're adding these spots by 2. So if you add the root 3/2 together, and then you subtract 1, you're gonna be left with this, right? Because you counted this twice and you counted this once. And then if you subtract the 1, you're gonna subtract all of this by 1. So then these are gonna be counted 0 times. And then this is gonna be counted 1 time. So if you add up the root 3/2s and then minus 1, you're gonna be left with the center length. And then so this center length is gonna be root 3 minus 1. And this is good because this is gonna be, the distance from E to G, that's a diagonal of our inside square, which means we can then use this to find what the side of our inside square is, which is just going to be this over root 2. And then to find our ratio, we just put this over the side of our larger square, which we set to 1, and we square this. But the over 1 does nothing, so we just square this. So then squaring that is just going to be 3 plus 1 minus 2 root 3 over 2, which is then going to be 2 minus root 3. And we can check if this is our answer. Wrong thing. Yeah, this is our answer, 2 minus root 3. Okay, so generally for this, I don't know, you just have to find like a clever way to do it, I guess. There's no really like systematic way to do it, I feel like. Anything you want to say there, Bill?
Yeah, I wouldn't say there isn't like a systematic way to do it because like in the end I think it's not there's not really like any other way that's like super fast. So besides this, that's like super obvious, at least to me. But I don't know. Maybe you can see something else.
Right, I just mean like for geometry problems like this, you just have to find like, I don't know.
Okay,
You,
yeah,
you,
yeah, makes sense. Okay, no, I get what you're saying.
uh, yeah, like I'm saying, like there's not like one method for all geometry problems to solve, not like quadratic equations or anything. But yeah, so just I don't know, for geometry problems like this, I guess my advice would just be uh just make sure to keep in mind like what you need to find in the diagram to get your answer, and then try to use geometrical tricks to arrive at like whatever you need and stuff. But really, it's a lot of it is going to depend on like what problem you're given, and you just kind of have to adapt to it for geometry problems. Okay, let's move on. Number 25. In a round robin chess tournament, every player plays one game with every other player. 5 participants withdrew after playing 2 games each. None of these players played a game against each other. A total of 220 games were played in the tournament. Including those who withdrew, how many players participated? Okay, so have a round robin chess tournament and people are playing against each other with one game with every other player. And then so they're playing normally, but after 5 people have played 2 games already, they withdrew and they did not play any games with each other. And then a total of 220 games were played. Okay, wait, does the 220 games count the games that were withdrew or not?
I think it does.
Okay. I guess we could just try something, and if it doesn't work, just assume the other one. Okay. So let's say we start with n players. Every player is going to play one game with every other player. So like if we're looking at one player, they're going to play n minus one games, right? And then we can multiply this by n to find the total number of games, but we're going to count every game twice, right? Because if Bob plays against Sally, we're going to count one from the game once from Bob's perspective and the game once from Sally's perspective. We're going to do that for all the games. So we need to divide n times n minus 1 by 2 to get the total number of games that were played. Or let n be the participants after 5 people have withdrew. Um, uh, okay, let n be the number of participants after the 5 people have withdrew. Let's think about the situation after the people have withdrew. After they've withdrew, every player is still gonna play every other player once. So we're still gonna have this number of games after they withdrew, and then before they withdrew, um they've played 2 games each with other people that are not themselves. Um, but the people that they played against, they're not going to be affected, right? Because they're still going to play against every other person. They just played against like an extra person, but they're still going to play against every other person. So basically, we're still going to count this n times n minus 1 over 2. And then the 5 participants that withdrew, they're going to give us an extra 10 games that were played before that these were counted, right? So then this is going to be our total number of games, which is 220. So basically, again, so n is going to be the number of people after 5 participants have withdrew. And then after the participants have withdrew, these n people are still all going to play against everyone else, right? That's going to be n times n minus 1 over 2 games. And then looking back at the games that are played with the withdrew people, we're just adding 10 games to this because these 10 games that they played, we're going to have to count that. And like the whoever that they played against, they're still going to be normally counted in this because they're still playing against every other player. So then this expression is going to be our total number of games. So then n times n minus 1 over 2 is 210. So then n times n minus 1 is 420. And then you need to find an integer n that works for this. And that integer n is going to be 21. So 21 times 20 is going to equal 420. So then n is going to equal 21. And again, n is, we set it equal to the number of players after 5 people have withdrew. So we need to add 5 to include those that withdrew. So then our answer is 26. Yeah, that's your answer. Sorry, I'm a bit, I don't know, rusty, I guess. We did these problems like a long time ago. But yeah, anything you want to say there, Bill?
Mm, Not really.
All right. Okay, the base 3 repeating decimal 0.12 repeating is equivalent to what base 10 common fraction? Okay, so usually in base 10, like if we have 0.86 repeating, how we convert this into a common base 10 fraction is we put this over 99, right? And I've talked about this um, in before meetings or in previous meetings. Well, I'll say it again, I guess. So if we have something like 0.9841, but only the 41 is repeating, what we're gonna do with this is we're gonna put this whole thing in the numerator, but we're gonna subtract the non-repeating part. The non-repeating part is 98. We're gonna subtract that, and we're gonna put this over the number of nines has to be equal to the number of digits that are repeating. So 2 nines for 2 digits that are repeating, and then we're going to add 2 zeros for the digits that are not repeating. So then this expression in base 10 would equal this stuff over 9900. Okay, in other bases, you apply like kind of the same thing. So instead of writing nines, you're gonna write whatever base it is minus 1. So in base 10, we put nines because it's 10 minus 1, which is 9. In base 3, we're gonna put 3 minus 1, which is 2. So we're gonna apply the same thing. We have 1, 2 repeating, so we're gonna put 1, 2 on the top. We minus 0 because there's nothing else that is not repeating. We put the number of 2's equal to the number of repeating digits, which is 2, right? Now we need to convert the numerator and denominator into base 10, and then we're going to simplify it. So 1, 2 in base 3 and base 10 is going to be 5. 2, 2 in base 3 in base 10 is going to be 8. But you can't simplify this, so then it's just going to be 5/8. That's going to be our answer. Yeah. Anything you want to see there, Bill?
I think I'm good. So, no.
Right. An arithmetic series of positive integers that has 8 terms, an arithmetic series of positive integers has 8 terms and a sum of 2008. What is the smallest possible value of any member of the series? Okay, we have an 8-term arithmetic series, has sum of 2008. We want it so that the smallest member has, we want it so that the smallest member of the series has the smallest possible value. So let's just say we want to give some variable names to our terms. Let's say our smallest term is x, and then our next 8 terms are going to have like a difference of d. So then our next term is going to be, it's going to be x plus d, and then x plus 2d. We're going to do this all the way to x plus 7d. And then the sum of the series is going to be ax plus, it's going to be 8 times 7 over 2 times d. This is just going to be 28. This is just applying like arithmetic series stuff on the 1 plus 2 plus dot 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 all the way to 7. It's just going to be the first and last sum times the number that there are, which is 7 over 2. Okay, and then so this is the sum, and we know it equals 2008. We want to minimize x, the smallest number of the series, right? So now we just have this expression. X and d are both integers, and we want to minimize x. So what we're going to want to do here is we're going to want to subtract as many 28s from 2008 as we can, but we want to keep it, or we want to subtract it, subtract as many 28s as we can, and then have our result of this side, or like, okay, sorry, or let's just put it as 8x equals 2008 minus 28d. Because we're minimizing x, we want this to be the smallest 0 mod 8 possible that we can have. So you want to subtract as many 28s from 2008 as you can while keeping it 0 mod 8. So now to do that, we want to analyze what this is in mod 8. So we know that 28 is 4 mod 8, right? Since 24 is 0 mod 8, since it's 3 times 8. We want to see what 2008 mod 8 is. So, we can just divide it by 8. Gonna get 408, then we're gonna get 8, so then it's 0. So 2008 is 0 mod 8. So we're doing 0 mod 8 minus 4 mod 8. So basically then, we have to subtract an even number of 28s. As long as we subtract an even number of 28s, this right expression is gonna be 0 mod 8. And subtracting an even number of 28s is just the same as subtracting any number of 2 times 28, which is 56. Which means that we can subtract any number of 56 to 2008 while keeping it 0 mod 8. And so now we're just left with the problem, how many 56 can we subtract from 2008? Well, let's just think of an estimate. 20 is going to put this at like 1, 112, 1, that much. So maybe it's going to be like in the mid-30s range. Let's try like 33. Okay, this is sprint, so we're going to need to be quick with this. So 56 times 33, this is going to be 168 times 3, or 168 times 11, sorry. And then this is just going to be 84181. 1848, we're a little bit short. Let's try adding 2 more 56s, which is 1112. Then we're at 016. No, this is 9. 161. Then we're at 1960. And then if we add another 56, this is going to be too big, right? So then the most amount you can subtract from 2008 is going to be 1960. And then this is going to give us 48. And this is 0 mod 8 like we expected. And this means that our minimum x is then going to equal 48 divided by 8, which is 6. And yeah, that is our answer. Anything you want to say there, Bill?
I mean, I guess like Austin's method of just like trying numbers was kind of tedious, I guess. I will personally just like go try 30.
Dividing?
Just like actually dividing would also work. Yeah, dividing would also work. But like if I was trying numbers, I would have just tried like 30, 40, and then 35 in between, because 35 it's gonna be like easier to multiply, I think.
I mean, yeah, I basically started at 33, so.
Yeah, 33. Yeah, that's also like an easy number to multiply. I felt like 30. Personally, for me, 35 would have been an easier number to multiply, but
Okay, I mean, that's just preference on multiplying stuff. So. But yeah, you could also divide and get it. Okay. Okay, number 28. How many whole numbers n such that 100 is less than or equal to n, which is less than or equal to 1000, have the same number of odd factors as even factors? Okay, so first we want to think of what what restraints are put on n when it says that n has the same number of odd factors as even factors? Um, so how I thought about this was looking at n's prime factorization. So prime factorization of n is going to be, I don't know, let's just say 2 to the a, 3 to the b, 5 to the c, 7 to the d, and so on. Now, the number of odd factors. So we can create odd factors of n by having this, by having 2 to the 0 times 3 to the, let's say, b1, and then 5 to the c1, 7 to the d1, and so on. As long as b1 is less than or equal to b, c1 is less than or equal to c, d1 is less than or equal to d, and so on. Basically just like, let's say we had some prime factorization, 2 times 3 squared times 5 times 7. I'm basically just saying, as long as we don't have a 2, we can take any exponents from this 3, 5, and 7, as long as it's less than or equal to our original exponents, then we will have an odd factor of our original number, right? And so the number of odd factors that we have then is going to be b plus 1 times c plus 1, or c1, b plus 1 times c plus 1 times d plus 1, and so on, right? Now for even factors, we want to include at least one, or this actually doesn't really matter, but whatever. For even factors, we want to include at least one factor of 2. So we can have it as 2 to the 1, and then we have 3 to the b1, 5 to the c1, 7 to the d1. But we can also have it as 2 squared, 3 to the b1, 5 to the c1, 7 to the d1. And we can have this so on. At least, as long as we have at least 1 power 2 in our thing, we will have an even factor of our n. But if we take our 2 to the first case, and then we have like whatever afterwards, this is going to result in the same number of factors as our odd factors with only 2 to the 0, right? Switching from 2 to the 0 to 2 to the 1, it's not going to change anything about anything else, and we could still have everything else as like whatever, right? So this part and this part are still going to have the same number of combinations, and so then we're just going to want, our only possibility of putting our 2's is 2 to the first, right? Like if we can only put 2 to the first, then we're going to have the same number of even factors as odd factors, right? This is going to be our even factors. This is going to be our odd factors. And this part and this part is going to be the same number of combinations. So then these two are going to have the same number of combinations, so the same number of even and odd factors. But if we could include 2 squared or more, right? Then we're going to have more of these, right? Like if we just have 2 squared and nothing else, then we're going to have exactly 2 times as many even factors as odd factors. But we want our even factors and odd factors to be the same, right? So then we only want to have the 2 to the first case. If we can only have the 2 to the first case, what does that mean? That means our initial prime factorization has one factor of 2, so that we can't put any more 2's into this. So then, in conclusion, for our n to have the same number of odd as even factors, we must have one and only one 2 in its prime factorization. Okay, so now that we have that condition, now we need to apply it to this range from 100 to 1000 inclusive. Now, if a number only has one factor of 2, that's the same thing as saying it's 2 mod 4, right? Because if it's 2 mod 4, it's going to have at least one factor of 2. And because it's not 0 mod 4, it doesn't have 2 or more factors of 2, right? So then anything 2 mod 4 is going to have one factor of 2. So basically then we can just find how many 2 mod 4 numbers are there between 100 and 1000. Now 100 and 1000 are 0 mod 4, right? 100 is 25 times 4, and 1000 is 250 times 4. And like we're basically going to separate this on mod 4s, right? So basically within every 4 interval, we're going to have one number that is 2 mod 4, right? So basically then we can just do 1000 minus 100 and then divide this by 4, and that should be our answer. So this is going to be 900. 900 divided by 4 is going to be it's going to be 250. And oh wait, 250. No, I did that wrong. Whoops. 900 divided by 4 is going to be 2 5. Yeah. No, I just did the end division wrong. Okay. So yeah, the answer is 225. Okay. Anything you want to say there, Bill?
No, I think you explained it very well.
Okay. Okay, let's move on. Okay, if x and y satisfy x minus 3 squared plus y minus 4 squared equals 49, what is the minimum possible value of x squared plus y squared? Okay. So you could try thinking of this algebraically. You could try expanding this expression and seeing if you can find anything special. So if we expand it, we have x squared minus 6x plus 9 plus y squared minus 8x plus 16 equals 49. And then maybe try to isolate the x squared plus y squared and combine the constants maybe. So we have x squared plus y squared minus 6x minus 8x. It's going to equal what? 40 minus 16, which is 24. And then you have x squared plus y squared equals 24 plus 6x plus 8x. And you're trying to find the minimum possible value of x squared plus y squared. This should be, whoops. Wait, this should be y. This should be y. This should be y. Okay. I think it's possible for you to solve it like this. But for me, I think it's a little bit weird. I don't know. You could probably still solve it like this. Maybe then with this, you can see. I don't know. I find this a little bit weird. Maybe you can solve it with this. But this is like an alternate method. But this is still kind of weird because you still have to have this stuff satisfying the original expression and that x squared plus y squared equals this. So it's a little bit weird. but the way I did it was noticing that the original expression is the equation of a circle, right? And it also has very nice numbers for the equation of a circle. So the top expression or equation is the equation of a circle with a vertex, or sorry, with a center at 3, 4 and a radius equal to 7. And um and then you can think of the equation as a graph of a circle where the center is at 3, 4, and the radius is 7. So maybe something like this. Not the best circle, but yeah. And then you can also think of x squared plus y squared graphically. X squared plus y squared at any point is going to be the length of, it's going to be the distance of this point to the origin, right? This is x, this is y, or it's gonna be this distance squared, right? With a Pythagorean theorem, this squared times, or this squared plus this squared is going to equal this squared. So basically, then we can think of x squared plus y squared graphically as the distance of a point to the origin squared, right? So then we can also use we can also use our equation, our graphed equation, and think about x squared plus y squared graphically to find its minimum. So we can think of the circle again, and now we can think of x squared plus y squared as we need to minimize the distance from a point on this circle to the origin. So now basically we turn this problem into a geometrical problem. We have this circle centered at 3, 4 and a radius of 7, and we need to find the shortest distance from a point on this circle to the origin. Now, if you think of a point inside a circle, maybe I'll put it like here. Any point inside a circle, and the center of the circle is right here. The closest point on the circle to this point is going to be on the line connecting connecting this point and the center of the circle, right? So the point is going to be on this line, and it's going to intersect with the circle here. This point is going to be the closest point on the circle that is to this point, right? That should be obvious just by symmetry, right? If we go any direction, this way or this way, we're going to be increasing the distance. And I don't know, this is just by symmetry, right? Like it wouldn't make any sense for the point to be on either side of this, because the circle is symmetric about this line, because because it's a circle, and this line is the diameter of the circle because it goes through the center of the circle. So then because of symmetry, it has to be either this point or this point. But then you just choose the closest point out of this, right? So in our thing, we were looking for the closest point on this circle to the origin, and the origin is just a point inside the circle, right? So then what we can do is we can draw a line from the center of our circle, which is at 3, 4, to the origin. And then wherever it intersects the circle over here, this is going to be the closest point that is to the origin. Now, this is going to be a radius of our circle, right? Because it goes through the center of our circle and it touches a point on our circle. So this whole distance is going to be equal to the length of our radius, which is 7. Now, we also know that the coordinate of our center is 3, 4, right? So this is 3 and this is 4, and this makes a right triangle. So then we know that this distance is 5, right? And because the whole distance we just said was 7, then this distance from the shortest, or then this distance from the closest point to our origin is going to be 2, right? And this is what we wanted, right? Because x squared plus y squared was going to be the distance squared, right? And this is also the distance of the shortest point, which we wanted, right? So then our minimum possible value of x squared plus y squared um, is going to be equal to 2 squared, which is 4. So then that should be your answer. And that is your answer. Also with the algebraic way, maybe you could have also seen that that from this equaling 6x plus 8y, then the ratio of I think this would mean that the ratio of y to x would have to be 6 to 8. So then y over x is 3/4, and then y is 3/4 x. So basically, I think you could have deduced this with algebra from right here. And then this is also saying that our shortest distance point, or our the point on our circle that gives us the least x squared plus y squared is also going to be on this line, which we also found it geometrically here, right? This was also the y equals 3/4 x line. Or actually, this is y equals 4/3 x line. Y equals 4/3 x. Actually, I'm not too sure about that. Yeah, I don't know. I think the algebraic way is a bit weirder, but whatever. Okay, but yeah, with this problem, I guess the takeaway was seeing that this equation can be modeled as a circle, and then making the x squared plus y squared also like a graphical expression, and then you can just solve it by like geometry. Anything you want to say there, Bill?
Um, I feel like you could like deduce the same thing algebraically.
Maybe.
I feel like you could deduce algebraically. I'm not. But I feel like you could. Like because you end up trying to just like minimize 6x plus 8y, right?
If you're trying to minimize 6x plus 8y, I feel like y over x would be 6/8, right?
6, 8. Well, if you're trying to minimize it, y over x, um,
But like the weird thing is
mhm.
you're trying to minimize 6x plus 8y, but your x and y still have to satisfy this expression. Right? Like if you're just, I don't know. Um, I feel like doing it algebraic is more It's more weird. I don't know. Maybe if it's easier for you to do algebraically, you can also do algebraically. Um, anything else you want to say on that?
Hmm. I mean, I guess just know the thing, know the circle equation. I don't really
Yeah.
have anything to say.
All right. Okay. Um, let's just move on then. Last question on our sprint. 8 identical unit cubes are stacked to form a 2 by 2 by 2 cube as shown. A short path from vertex A to vertex B is defined as one that contains or that consists of 6 one-unit moves either right, up, or back along any of the 6 faces of the 2-unit cube. How many short paths are possible? Okay, so we have 6 moves. Um, we have 6 one-unit moves, and we're moving on any of the faces of the 2-unit cube, and we want to get from A to B. Um, it says the 61 unit moves is either right, up, or back, but I think that is confusing, right? Like depending on which direction you're facing, your right, up, and back is going to be different. And back is weird, right? Back we don't know if it's talking about like like down or left, like right or up, like which ops. But basically like we just assume like you can like go in any direction. Right? Or could you interpret this, Bill? Right, up, or back?
Okay, so for this problem, because it says a short path is defined as one that consists of 6 one-unit moves, so 6. The only way for you to move, or only way for you to get from A to B in 6 one-unit moves is if like you go straight there and you're not like turning back at all. So
Yeah, so there's only like 3 possible
there's only 3
directions.
possible
Right.
directions for you to go in if it's like that.
Right, and it says like 3 things, like right, up, or back. So then you can just like say, like I guess like you can just say like that they are saying like you can go in any of those 3 directions. So basically, then you can go in any direction basically, since like you can only go in 3 directions to actually get a short path. Um, okay, so we want to find out how many of these short paths are possible. Let's define like a axis system just to talk about this better instead of like right, upper, back, because that's going to be confusing. So I'm going to draw 3 axes here, and let's just label this x, y, and z, and this is you know have this like point A's here and have the axes like this. So, if we're going in this direction, let's call it, we're going in the positive x direction. And then, if we're going in this direction, we're going in the positive y direction. If we're going in this direction, we're going in the positive z direction. And it should be pretty obvious that we can only go in the positive directions of these because, again, because we only have 6 moves, we have to go straight there. We can't go backwards on any of these. It would we don't have enough moves for that. So we can only go positive in any of these directions and just call them x, y, and z. Okay. One way you can do this is think of just our xy plane. Don't think about our z axis yet. So look at our xy plane like here. So A is here and B is here, but B is really like 2z units above this, right? But just think of B here on the xy graph for now. And so, this is positive x, this is positive y. And then this is going to form a 2 by 2 grid. So you can think of our path as a path on our 2D xy graph. So like here. But we need to include 2 upward z moves somewhere along this path, because we need to have 2 z moves, 2 positive z moves to get to B. And you can think of we're including it on this path somewhere, right? So if this is our base like xy path, we can include our upward z somewhere. We can have either 2 z's, 2 up z's here. So we go here, we go positive x here, we go 2 up z's here, and then we continue along our xy path. Or we can have our plus z's somewhere else too. We can have it here, and then we can have it here. So another path that we could take is we can go 2 positive x's, then a positive z, then a positive y, then a positive z, and then lastly a positive y. So basically, we want to try to think of how many ways we can arrange that. And the number of ways we can arrange that is going to be the number of short paths that we can make. So just like thinking of it 2D like that can maybe help simplify the problem a little bit, instead of thinking like you're traveling along the faces. But there is one condition that we have to be careful of here, and that is that we can't go inside the circle, or the cube. Basically, like if our path is something like this on the xy plane, we can't have positive z's coming out from this center vertex, because that would then mean our path is going inside the cube, but we want to always travel along the faces. So we can't have a positive z in this middle point here. But as long as we don't have that, then we're going to be moving along the faces, and whatever combination we have is going to be valid. Okay, so hopefully that makes sense. Just let us know if it doesn't. Okay. So now we want to find these combinations, but keep in mind we can't have positive z's in the center. Okay, so now we can separate our xy paths into 2 types of paths. One type is a path that does not go through the center, and which is like one like this, and one is that it goes through the center, which is one like that. So the number of paths that so like those paths are different because the edge paths don't go through the center, so the z can the plus z moves can be on any of those vertices. While if we're looking at a center path, it can only be on 4 out of all 5 of the vertices, right? So basically we're doing like casework on those type of paths. So now let's first count how many of each path we have, right? So we have 2 edge paths. We have one that's this and one that's that. So 2 edge, I'll just list that here. And then how many center do we have? Well, we can go like this, that's one center. We can also go like this, that's another center. And we can go like this, that's another center, and our last center is going to be like that. So we're going to have four center paths. And also a way to check if you've counted all the paths like this is to think of the total number of paths you can have on a 2 by 2 square, and you're only moving up and right, right? You know, so then you're arranging two up moves and two right moves um, within this, and it can be any order, right? So then you're just arranging this for every combination. So then it would just be 4 choose 2. So your total number of paths would be 4 times 3 over 2, which is 6. And that makes sense, right? Because we counted 6 total moves. So I don't know, that's just a way to check if you've counted all of your moves correctly. Okay. Now that we have this, we can look at the edge and the center paths respectively and see how many ways there are to arrange the z's. And you know how many ways there are to arrange the z's is going to be how many total short paths we can get out of this type of path on our xy plane. So let's look at one edge path here. Our z's can be on any of these vertices. A, here, 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 or B. Now, it's not going to be 5 times 5, right? It's not just going to be, you know, we have five five possibilities for each, like where to place each positive z move. So then it's just going to be 5 times 5. It's not going to be that, right? Because like if you stack the z's on one vertex, this case is going to be kind of twice, right? You know, one time you're going to count, you know, placing this first and then placing this on top, and one time you're going to count like doing the opposite, right? But like there's still both on this, so then you're counting it twice, but you know you still have the same move of going twice up on this. So 5 times 5 is not going to work here. Now you could adjust it um, so that you know for every one of these you don't you subtract 1 for every overcount that you have. So then I believe you can do 5 times 5, but you're going to subtract 1 for each overcount. Each overcount that you have is going to be the number of 2 ops that you have, which is 5. So it would just be 5 times 5 minus 5, right? Wait. Wait, no, it's not gonna be that because
Right. It
like you're
wouldn't
still
be.
gonna count. Yep.
Yeah. Because I mean, 5 times 5 minus 5. I mean, 5 times 5. The ones that are repeated are the ones that are not on the same dots. The ones that aren't, when there's two on the same ones, they are repeated. Wait, they aren't?
Uh,
You can keep going.
wait, I'm thinking. You can keep going.
Oh no, it's fine. You can go.
No, I was just thinking. Wait, why aren't the double vertices gonna be repeated?
The,
Am I
sorry, the what?
like if you had two z's on a vertex,
Hmm.
would that not be repeated?
That wouldn't be repeated because think about it. How would you repeat that? There's only one way to get that, right?
Oh, okay, okay. I think I get it now.
Yeah, I think this is like a misunderstanding like a lot of people have when they're doing like counting problems like this. Is that the ones that are on the same
Yeah.
dot, they're not repeated. It's the ones that are not on the same vertice that are repeated.
No, yeah, that is right. So like, okay, let me explain it a little bit further. So yeah, Bill is right. You if you have like two z's on different vertices, this can be repeated because like it's like if we label these 1, 2, 3, 4, 5, it's like we can get either then it's like we're rolling dice with 5 faces. And then this is going to be repeated because we can get a 2, 3, and then that would work. We can also get a 3, 2, and that would work. And these are two different cases, so then we're overcounting it. Like two different cases for the dice, but one case actual for our paths. So then we're overcounting that. But if we have two on the same vertice, um, I don't want to erase. I guess I'll erase. Okay. 1, 2, 3, 4, 5. Okay, but if we have two on the same vertice, like this, then we're not overcounting it, right? Because there's only one way to do this, which is to get 3, 3 on our dice rolls, and you can't arrange this in any other way. So the ones that we are overcounting is the ones that are not doubled, but we can't adjust for that. So we're counting 5. These are 5. The 5 vertice ones, the 5 double vertice ones, we're not overcounting, right? But the other 20 cases out of our total 25, we are overcounting it by like double, right? So then we can divide our 20 cases by 2, which should then give us 10 actual cases. And these are counted, these are not overcounted. So then we just have 5 plus 10 equals 15 as our total cases for this. So then we have 15 for each of our for each of our edge cases. You can also do this with stars and bars. So with stars and bars, you can think of the paths as the stars and the bars as the z moves, the plus z moves. So you know we have a we have a move here. So this goes okay. Let's just call our moves like x x y, right. We go x and then y and then y. So we can think of these as our stars and our bars as our z things. So we're putting bars like we can have 2 bars here, or we can have bars here. So it's like in between the paths because our z moves are on the vertices, which are in between our paths. So then we can also we can also think of this. So then we have 4 stars and 4 stars and 6 total things to arrange because we have 2 bars. So then our expression would be 6 choose 2, which would be 6 times 5 over 2, which is also 15, which is what we got before. We should not be overcounting anything here because we are saying that the bars are the same and we're like choosing we're choosing the position of the bars. We're not doing permutations of them. So we wouldn't be overcounting here. Anything you want to say about that, Bill? The stars and
Yeah, this is
bars.
kind of like a modified use case of stars and bars. Um, but yeah, it is stars and bars. So this is kind of something that you'll just notice by like having used stars and bars a lot and like kind of understanding what's happening when you do stars and bars. And like I guess just like more flexible usage of stars and bars, I guess. But yeah, this is kind of just knowing that stars and when you do stars and bars, you're basically like inserting just mm, yeah.
Yeah. Yeah, this is a use of stars and bars. I don't know. You can also do it like this if you notice it.
So yeah, this is kind of like the use of stars
Yeah.
and bars where you're putting like a certain number of things into like a certain number of groups. Like I always think of like eggs and baskets. You have a certain number of eggs, and you have to find
Eggs and
ways to.
baskets.
Yeah, that's how I always think of them. You have a certain number of eggs, and you have to put them in a certain number of baskets.
But like you're arranging the stars and bars, but the baskets are like I don't know.
Yeah, that's how I always think of these like this kind of like thing. It's eggs and
Mm,
baskets.
okay, but yeah, you can just do either method. Okay, so either method, and then you get 15 cases for your edge cases. Now we need to look at the center cases. Let me just draw a new 2 by 2 for this. So let's just draw a center case that looks like this. So our z moves cannot be on this vertex, right? Because then our path would go inside the cube, and we can't have that. We can only travel on the faces. So then our z paths can or our z moves can only be on these 4 vertices. Now they have to be like on like so if we have one z move on this vertex, the other z move has to be on this same side as the other z move. So then our other z move can only be this, or it could be this. Why is because if we have our z move on the different side, this side, if our path looked like this, think about this on the cube. We would be going up once on the A, and then we go through so then we go 1x, and then we go 2y's. But because we're going 2y's on here, we're going through the cube. And that was because we only went up one, we only had one z move, right? And that caused our y move to go through the cube. And because this is a center path, it's always going to go through the center. So basically, we're going to have to need 2 moves before we go to either 2 or 0 z moves before we go through the center, so that we also don't go through the middle of our cube. So then that would mean that our z moves have to be on the same side, either on this side or either on this side. This also applies if our center path was a little bit different. It also applies if our center path looked like this, right? It's still going to be the same. We're still going to travel through the center. We either want 0 or all 2 z moves to be on this side. So then basically it's either both z moves are on this side or both z moves are on this side. So same thing as the other case. Okay, so then let's think about how many ways we can have that, right? So this is just very easy counting, right? We can have either both of them on here, both of them on here, or one on here and one on here. So that's 3 cases for one side, and the other side is identical, right? So then we have also 3 cases for this side. So then in total for our center path, we have 6 cases. So then we just multiply these numbers. We're going to have 2 times 15 plus 4 times 6, which is then going to be 30 plus 24, which is then 54. And this is our answer. Anything you want to say there, Bill?
So another way you might have been able to do this was if you like flatten the thing out, like flatten the what is it? Flatten the surfaces out. I feel like you might have been able to do it that way. So like say you only use like the left and top side, like the line will only go through those sides. You might have been able to do it that way. If you were to do it like that, um, what do you think, Austin? Do you think if you did it like
Uh,
that, do you think you would have been able to do it? Do you think? So that would be
um,
5 choose 2. 5 choose 2, and then that's multiplied by 1, 2, 3, 4. Ooh, and then 5,
I think it's possible, but it's a bit complicated, I think.
6
The complicated thing about it is um like like looking at these sides, if you're using this left side and this right side and this left side and this top side, so you look at it like this A, B is here, and you also have it like this and what A and B is here. Do it this way. If you want to do it this way, sure, but we'll just leave it as that. At that. Okay, that was all of 2014 sprint. Been kind of slow there. Maybe we should go a little bit faster, but I don't know. The problems were maybe a little bit rough. But yeah. Okay. Wait, do you need to restart the recording, Bill, or is it fine?
Oh, I think it's fine.
Okay. Okay, now we're doing target.
Well, we only have 5
Hopefully,
minutes left, so
what?
it's okay. Go.
Okay. So number one, two sides of a right triangle are 9 units and 12 units. What is the numerical value of the product of the two possible lengths of the third side? Express your answer in simplest radical form. Okay, so why it says possible is because, these two sides, don't have to be necessarily the legs, but they can be, any combination of the sides of the right triangle. So let's say combinations, right? We can have 9, 12 as our legs. And then, what would be the value of the third side? Well, 9 is just 3 times 3, 12 is just 3 times 4. Then we have 3, 4, 5 scaled by 3, so then this would have to be 15, right? So one of our cases, 15 is our third side. Now, another case that we can have is 9 is the hypotenuse. Or, sorry, 12 is the hypotenuse, and 9 is the leg. So why we can't have 9 as a hypotenuse and 12 as a leg is because the hypotenuse always has to be larger than either of the legs. So then this is our only second case. So then let's find what the third side is. It's going to be, by the Pythagorean theorem, it's going to be 12 squared minus 9 squared, which is 144, minus 81, which is equal to 60 square root of 63. And then we can take out a 9 from this, and it would be 3 root 7. So then our two third side lengths are 15 and 3 root 7. So then we multiply these together, and we have 45 root 7. Simplest radical form. That is correct. That is our answer. Okay, we have 2 minutes left. Let's just get done with this problem. 3 unique points are chosen at random from the vertices of a convex octagon. What is the probability that they form a triangle, none of whose sides is the side of the octagon? Express your answer as a common fraction. Okay. Choosing 3 unique points on an octagon, and we need to find the probability that it forms a triangle, but the triangle cannot have any sides that are a side of the octagon. One way you can do this is you can count how many total number of triangles you can have with none of the sides being on the octagon. Then you can also count how many ways you can choose 3 unique points on the octagon, and then the ratio of those two would be your answer. So how we can count the total number of triangles that satisfy this, that don't have a side that coincides with the octagon. We can think of first the shape of the triangle, and then think of rotating it. So one shape that we can have, let's think of our smallest triangle shape that we can have here, right? And that would be this. That would just be skipping one vertice on like each of these sides, right? So I'm going to call this my 2, 2, 4 triangle, because these vertices are separated by 2 side lengths. These are separated by 2, and this is separated by 4. So this is my 2, 2, 4 triangle. Now, how many 2, 2, 4s can I have in my octagon? Well, I can rotate this 8 times, right? So then I'm going to have 8 2, 2, 4 triangles. Now, are there any other types of triangles I can have? Yes. I can't draw an octagon though. Here, I'll just use the same thing. Another type we can have is this. This is a 2, 3, 3 triangle. 2, 3, 3. And I can also rotate this 8 times. Be careful that there is no like rotational symmetry, because then you would have to like divide this by 2 or something. But for our 2, 2, 4 and our 2, 3, 3, there is no rotational symmetry. And then this is it. There's no other types of triangles that you can have while having like the sides not coincide with the octagon. So that means our total number of triangles is going to be 16. How many ways can we choose our 3 points out of 8 points? Well, that's just going to be a choose 3. It's just going to be equal to 8 times 7 times 6 over 3 factorial. But 3 factorial is just 6. So we can cancel this out. This equals 56. So then our probability is going to be 16 over 56. And why this works is because, like, you know, each of our each triangle case that we counted is going to be like a different case in our 3 unique points, right? Okay, so then 16 over 56, we can cancel out an 8 on top and bottom. So then we have 2 over 7. And then that is our answer. 2 sevenths. Okay. That's going to be it for this meeting. Thank you for coming, and we will continue from here next week. Good to see you, and goodbye.